Hello, in this video we will be exploring how we quantify the strength of acids and specifically what kinds of acid, and bases as well. So typically the way that we measure the strength of a Bronsted-Lowry acid or a Bronsted-Lowry base is as follows. For a Bronsted-Lowry acid, the way we measure the strength of that acid is we take that acid in water with water acting as the Bronsted-Lowry base, and we allow it to ionize to form the conjugate base of that acid and hydronium. Okay, so there is our reaction, right? So we're looking at the ability for our acid, HA+, to donate H+ to the Bronsted-Lowry base and convert itself to the Bronsted-Lowry acid. This should look familiar, right? You'll note these arrows that I drew here. For all but strong acids, these types of exchanges form chemical equilibria, sometimes more, and they're typically less than 1. And so let's write what the equilibrium expression would look like for this particular reaction, as we learned how to write them in a previous chapter. So we take our products. So we have our concentration of our conjugate base, A- aqueous to the first power. Then we have our concentration of our H3O+, our other product, aqueous to the first power, all over the equilibrium concentration of our unionized Bronsted-Lowry acid. Now you'll note we exclude water because it is a pure liquid. This particular reaction, acid plus water forms conjugate base plus H3O+, and this equilibrium expression, this is known as a Ka, or an acid ionization, although sometimes it's referred to as an acid dissociation, although I do not like that designation. This is an ionization, an acid ionization constant. Okay, acid ionization, it's a special K. So what we're going to be learning in this chapter and the next chapter is that for specific equilibria that have the same way that you write it for specific types of chemical compounds, we can give names to those chemical equilibria and their equilibrium expressions, right? So this is the acid ionization constant, okay? Now we could do the same thing. Well, first of all, sorry, I'm getting ahead of myself. A larger Ka means a stronger acid. Okay? A larger Ka means a stronger acid. Weak acids have Ka values less than 1, meaning weak acids are reactant favored. Meaning at equilibrium, right? Our ratio is less than 1 of our products to reactants, right? Strong acids, and we'll talk about those more later, much greater than 1 typically, thus product favored. However, we're going to find that we cannot typically measure these in water, but that's something we'll talk about much later. right? We care more about these weak acids, as pretty much all other acids are weak acids. Remember what our strong acids are. You need to memorize these: HCl, HBr, HI, HNO3, and the first proton, so the first ionization of H2SO4. And then, of course, there is one last one, but you don't really need to know it, or we tend not to test it. But if your instructor says that you need to know it, memorize it. Perchloric acid, HClO4. Everything else, any other acid, is assumed to be weak and thus will have a Ka value less than 1. Oftentimes, significantly less than 1, as we're going to see. Well, let's give some examples here, right? So the Ka for acetic acid, C2H3O2. However, oftentimes this is written as CH3COOH. It's the same thing, right? There's the ionizable proton, okay? It has a Ka value of 1.8 times 10 to the negative fifth at 25 degrees Celsius. Okay, remember all equilibrium constants are only true at a specific temperature because changing temperature changes the equilibrium constant. Okay, let's look at another acid. Let's look at carbonic acid. Okay, so the first proton of carbonic acid, because it has two, we'll talk about that here in just a moment, 4.2 times 10 to the negative seventh at 25 degrees Celsius. Right, so you'll note that's even weaker than acetic acid. Okay? All right. There's something else we'll talk about later, but with increasing Ka and increasing strength of acid, we get an increase in the percent ionization typically. Okay? So stronger acids, greater percent ionization. We're going to learn that percent ionization, so percent acid ionization, but we'll look at this more a little bit later, is going to be the concentration of produced H3O plus at equilibrium divided by the initial concentration of your acid times 100, right? So actually, no, it's not even H3O plus. Technically, it's A minus, the conjugate base, right? So in other words, either H3O plus or A minus, it's the percentage of it that has, or sorry, the amount that has ionized divided by the initial total amount of that acid times 100%, acid ionization. Okay. Now we can do all of the same stuff for bases. So generically for Bronsted-Lowry bases, I'll just use B. And so again, we can take our Bronsted-Lowry base and we're going to measure its strength as a base, again, in water. I'm writing it in red here to show that it is acting as an acid. And again, the vast majority of bases are going to be weak bases. Strong bases tend to be things that are very, very, they are things that are do not typically want to lose a proton, and therefore, if you find a way with great effort to remove a proton from this thing, then what's left over is a very, 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 very strong conjugate acid that will be very product favored. Anyway, in this case now, the water is donating the proton to the base. Or you could look at it as the base is accepting the proton from the water. Still an ionization because now the water is what's ionizing, right? That's separating into two ions. And so that leaves behind HB plus and OH minus. And so just like we had a Ka, lowercase a, meaning the acid ionization constant, acid ionization constant, this will be the base ionization, or again, sometimes referred to as dissociation constant. So K, lowercase b. And so here, let's copy these, move them down here. That way I can just rearrange, okay? So it is going to be, again, products, concentrations of products, divided by concentrations of reactants. Put my little, at equilibrium, of course. So equilibrium, all to the first power, because proton transfer reactions have the stoichiometry 1 to 1 to 1 to 1. Makes things a little bit easier than it was in chapter 17. Okay, so here is our base ionization constant. And to give you an idea of some KBs, so the KB for NH3 ammonia is 1.8 times 10 to the negative fifth, right? That's a measure of its ability to strip a proton off of water. And again, note with increasing KB, that is a stronger Bronsted-Lowry base. Okay. And again, the greater KB is, the greater the percent ionization is that occurs. And it's the same deal as before. The percent ionization for the percent base ionization is going to be the concentration, the equilibrium concentration of HB plus over the initial concentration of B times 100. We'll talk about equilibrium initial and deal with ice tables, which you first saw in chapter 17 all throughout chapter 18, but we'll do that in a separate video. Okay, so again, stronger bases, more ionization, right? Stronger base, more molecules of water at equilibrium have been deprotonated to protonate the base and form its conjugate acid form. Okay, so this is Ka and Kb, right? Two of our new, so Ka and Kb. And again, note, Ka is a very specific reaction. Ha plus water forms A minus plus H3O plus. A could be anything, so it could be HC2H3O2 plus water forms C2H3O2 minus plus H3O plus. Actually, let's look at an example of that real quick, right? So if we were to write the equilibrium expression for this HC2H3O2, and so I have the Ka for it. So what does that reaction look like that Ka represents? Well, it's that plus water forms the conjugate base HCO3 back up here. C2H3O2 minus aqueous plus H3O plus aqueous. So that is the specific equilibrium expression for the single ionization, single deprotonation of acetic acid. Here's H2CO3, right? H2CO3 aqueous plus H2O. Again, the water is acting as the base if the acid is acting as the acid. So we strip off a proton, we end up with HCO3 minus, because remember, even though there are two ionizable protons, our acid-base chemistry here is single proton transfer. So we write one at a time. And we're going to look at that in just a moment. Okay, so there's what our Ka reactions look like for the Ka expression it represents. And we can do the same thing for Kb's, right? Here's our NH3. So we can have NH3 aqueous plus water. Remember, for bases and looking at their ability as a base, we use water as a reference point. So just note, for all of these, we look at ability of thing to donate to or accept from, in the case of a base, water. Okay, Ka, Kb. Always water, always water. It's referring to this specific reaction. Okay, so anyway, let's continue this here. So we have our Bronsted-Lowry base. It is going to accept a proton from the water. The water is going to act as the acid, donate the proton, and so we end up with NH4 plus. Okay, be careful with these, right? Your typical weak bases are typically going to be of the formula like R2NH or RNH2. R could be anything. R is just indicating that there could be other things attached. And so for amine bases, as these are called, these are all amine bases. Ammonia is one of them, right? The conjugate acid form of these, oops, I made a boo-boo. That should just be NR3. Okay, because we should only have three things on the nitrogen before we form the conjugate acid. So R3NH plus, R2NH2 plus, RNH3 plus, and of course NH4 plus. So just to give you an idea, right? We write those things quite a bit differently than we write acids. The H's are going to tend to be on the right side of the nitrogen, unlike for acids where the H is on the left side of the chemical formula. Anyway, to complete this reaction for the Kb expression, NH3 plus H2O forms NH4 plus, and of course, OH minus the conjugate base of water. All right. So we've already presented that our acids can have more than one ionizable proton. So let's look at this real quick. So I'm going to make some copies of this. I'm going to need 3 of those guys there. Okay, and so let's look at phosphoric acid. Okay, phosphoric acid. Well, we could deprotonate and make HPO4 minus aqueous. That would be the conjugate base of H3PO4, forming H3O plus. Duplicate that twice because we're going to need them here in just a moment. Okay. But this should be H2PO4 minus. But that H2PO4 minus, even though we've written it as the conjugate base, in the right environment, it could lose another proton. Acting as an acid again with another equivalent of water. So now its conjugate base is HPO4 2 minus. And then, of course, we generate another equivalent of H3O plus. And then yet again, we still have one more ionizable proton left here on the HPO4 2 minus that could then, again, in the right environment, act as a Bronsted-Lowry acid in the presence of a Bronsted-Lowry base, such as water, to form its final form, okay, the least protonated form of it. Thus, it cannot ionize again, right? There is no additional There are no more protons to remove, right? And our last equivalent of H3O plus. Okay, so this is called and you've heard me say it before, but a polyprotic acid, right? Poly, many, protic, H plus. So this is an acid that can produce per molecule more than one H plus, more than one H plus it can donate. Okay, and so phosphoric acid here is you could call it a triprotic acid. It has 3 ionizable protons, and that means it's going to have 3 Ka values, one for each of these proton transfers, right? One for a loss of a proton from H3PO4, one for the loss of a proton from H2PO4 minus, and one for the loss of a proton from HPO4 2 minus, right? I'm not going to write the equilibrium expressions here, but you could write the equilibrium expressions for each one, right? So for the first one, for example, it's going to be our H2PO4 minus H3O plus all over H3PO4 and so on, right? We can actually, let's just go ahead and do it real quick. It's good practice, right? HPO4 2 minus H3O plus over H2PO4 minus. These are all at equilibrium. And then lastly, PO4 3 minus the simple phosphate ion H3O plus and HPO4 2 minus. So, what you need to understand here is, generally speaking, for polyprotic acid, the first acid ionization constant is going to tend to be much higher than the second, which will be much higher than the third. Because as you remove protons, it's harder to remove the next proton. Because, well, for many reasons, it has to do with electronics and electron density. Basically, for each proton you remove, you can think of it as the remaining covalently bonded hydrogens that are ionizable, the bond gets stronger. Okay, the bond gets stronger, and thus it's harder to remove the next ionizable proton from it, right? So the first proton that you remove from phosphate is the H3 phosphoric acid is the easiest to remove. Then if you try to remove the second proton from H2PO4 minus, it's harder. And then that last proton is the hardest to pull off. And so let's see what that looks like in terms of Kas, because remember, Kas are a measure of this ability, right? What does the equilibrium look like in water for this acid, protonated water to form hydronium ions? So for Ka1, the first ionizable proton, 7.2 times 10 to the negative third, right? Not too far from 1. We're going to see there are many acids that are much weaker, 10 to the negative fifth, 10 to the negative eighth. Okay, so not super weak, but still a weak acid. Our next one, though, 6.3 times 10 to the negative eighth. I want to point that out here. Going from a 10 to the negative third to a 10 to the negative eighth is 10 to the fifth, right? That is a decrease by a factor of 100,000 in the equilibrium constant, right? 10 to the fifth is a 1 with 5 zeros, right? So it's 1,000 times lower in terms of orders of magnitude. Well, it's 5 orders of magnitude, but in terms of direct, it's 1,000 times lower Ka value, right? And then if we look at Ka3, we see that's 4.2 times 10 to the negative 13th. Okay. And so we're going from 10 to the 8th to 10 to the negative 13th. You guessed it. It's another 10 to the 5th. Another 100,000 times. Right? What we're showing here is that because because the ability to remove protons, the next proton uh, becomes hampered. It gets harder and harder to remove the next proton. The amount of H3O plus that will be produced, actually just the amount of products that will be produced, will be significantly less than the first ionization, right? So your products of your second ionization are going to be very, very, very tiny relative to the products of that first ionization. And your products of your third ionization are going to be virtually zero, right, relative to that first ionization. And so therefore, typically for polyprotic acids in calculations, as we'll see later, we're only going to care about the first ionization. Because the additional ionizations just are very, very, very reactant favored. Very little product forms. And then in the third one, in this case, it's virtually zero, right? We can write a number for it. It's a potentially measurable number, but relative to the concentrations and the acid ionization constant for our first ionization, it's zero. So anytime you have polyprotic acid, we're going to look at calculations here in a little bit. You only need to worry about the first equilibrium, that first acid ionization. All of the other ionizable protons on that molecule are going to be so much harder to remove that, and so reactant favored, that the amount of product that they produce is measurable, but has virtually no impact on the rest of your calculations. So we can just ignore them. Okay. And you can do the math. You could do the math to see, okay, well, we learned in chapter 17, Ka1 leads into Ka2, leads into Ka3. So K total, right? Ka total would be just the first one times the second one times the third one. Okay. And that would be the new K value. And ultimately, we would find out that our equilibrium concentrations are going to really be no different for H3O plus for the first ionization versus taking all three into account, because the second, third ionization are going to produce so little H3O plus, which is what we care about, as we're going to see in this chapter. Okay, so that concludes a discussion of Ka, Kb, and polyprotic acids.